all know that weaving is an ancient craft and technology which has been around for thousands of years. This slide presents some representational woven pieces from ancient China, Africa, and Egypt. So traditional hand weaving has always been a very slow process which requires a lot of time and labor. One single piece can take the artisans months or even years to complete. So during the Industrial Revolution, Jacquard weaving technology was invented by Joseph Marie Jacquard in the early 19th century. It transformed weaving manufacture from craft to industry production. So the weaving manufacture speed has been largely increased with the invention of Jacquard technology. Up to today, in this digital age that we're living in, weaving industry is embracing its new life. In 2016, Google partnered with Levi's to create a new interface, interactive interface, which allows the user to wirelessly control their smartphones just by touching their clothes. Textile materials, as the most intimate materials in people's daily lives, have achieved new performance and design values during the past decades through the integration of advanced technologies. Particularly, smart photonic textiles has been given the capability to display illuminative colors, patterns, and texts from light emissions and has been adopted in different applications ranging from fashion design, home furnishing, healthcare, and safety uses. So my work will focus on one type of the smart textiles, which is POF textiles, shortened for polymeric optical fiber textiles. POF textiles are produced by directly integrating optical fibers into the textile fabrication process, thereby providing unlimited possibilities in terms of surface design and tactility. It shows its advantages of lightweight, low cost, flexibility, and low power supply in comparison with the other types of photonic textiles, such as LED embedded photonic textiles. The surface light emission is enabled by microbending of POFs or cladding damages to POFs. However, it is important to be aware that POFs can be susceptible to damages from severe bending, which is one of the major challenges. The fabrication methods include embroidery, knitting, and weaving has employed by practitioners and researchers to produce the POF textiles. However, the fabrication methods of knitting and embroidery require looping yarns, which can damage the POFs due to severe bending, which will lead to very short light travel distance. By contrast, woven textiles are formed by interlacing yarns with one another. This process involves less bending. Hence, it causes less damages to POFs. Therefore, weaving technology is more suitable for producing larger-scale POF textiles. And some POF textiles and prototypes have been designed, developed, including some prototypes by Dr. Jeannie Tan and then Ziqian Bai. However, the prototypes is quite bulky and needs more variation in terms of appearance and tactility. And furthermore, the preparation process is still very time-consuming, which prevents it from adapting for the mass production. And then some other photonic textiles integrated with optical fibers have also been developed by other designers and studios, including Malimbo Baktada, XX Labs, Dreamlocks, and Zach Poser. So based on the review of existing works in the field of POF textiles, we can see that the new functions are enabled for POF textiles with the integration of electronic textiles. However, the integrated electronic components add to the bulkiness of the design, which affects the usability and appearance. And then the electronic connection process is still laborious and time-consuming. And weaving plays a very important role in the development, however, has been neglected from the existing research. So, and then the current POF textiles are still, the properties are still rather limited, and most of them are still in planar and then the single layer form. So more complex woven structures with multi-layer should be developed for new design solutions for the electronic integration as well as the enhancement for the new properties. So as we know that So for the POF textiles, there are new design elements such as conductive yarns, power supply, microcontrol system, LED, and optical fibers that are integrated, which is very different from the traditional jacquard weaving fabrication process. So there are new design challenges and that we incur for the development of POF textiles. So from the weaver's perspective, there are three main aspects, including for the new challenges, including the optimizing new performance, integrating with electronics, and seamlessly and placing the functional yarns to meet both aesthetic and technical requirements. So here I'm going to present four major challenges for my research, which covers the seamless electronic integration and new properties for POF textiles, and then the weave design for multisensory environment. So the first design challenge is to overcome is to develop a new weave design method to achieve more seamless electronic integration. So in order to connect with the electronics, POF fringes need to be created and separated from the rest of the yarn system. So the previous method of creating the POF fringes require manual labor, and it's it is very laborious and time-consuming. So I created this this three-dimensional compound weave using the floating technique, which enables the automatic separation of the POF floats and then the other textile-based yarns directly via the jacquard weaving fabrication process. So this new weave technique have eased the electronic connection, and it enables the development of POF textiles in one process, and which has significantly reduced the time and labor. However, this new weave solution have cause more issues during the weave production process, because it causes the great difference in the work tension between the center motif and then the POF fringe areas, which has slowed down the weaving production process with the a lot more like dropped wires. So in order to solve this production issue, a more balanced weave combination has been designed for smooth weaving production, which is illustrated on the left of the slide. In addition, a lock section woven with plain weave is designed in between the center motif and the POF fringes to avoid the POF fiber slippage. And then the next experiment have successfully fabricated the POF textiles with new property of three-dimensional effect and stretchability. And so the three-dimensional effect of POF textiles have increased the diversity in aesthetic and tactility, and it also offer more versatile visual and tactile experience for the users during the interaction. And then the new property of stretchability has contributed to increase the comfort and flexibility for POF textiles. And then, so these new properties are enabled by using the double weave combined with spandex and suitable motifs. So the motif was designed in weavy pattern to allow for the space for spandex to shrink. And then the stitched double weave and then is alternated with unstitched double weave. And as we can see on the left right corner, and then the white space, the white section is designed with unstitched double weave, and then the black section is designed with a stitched double weave. So the spandex at the unstitched double weave section can shrink at the bottom with the POF puckering out on the top, which create this three-dimensional effect. And and then the weave design is also shown in the diagram on the right side with the cross-sectional view as well. And then this is this is how this new PUF design, how this design is applied onto fashion pieces. And then the next design challenge is to enhance the touch sensitive function of PUF textiles. And then two interactive cushions are developed, which are named Sensi and Cappy. And several major weave design aspects are tackled, including the design for capacitive sensing areas, and then the design for the surface textures and interactive sections, and as well as the electronic connection, and then more balanced weave combination for smooth production. So the touch sensing ability is enabled by directly weaving conductive yarns at the designated areas, which replace the foil paper in the previous prototypes. For cushion cappy, 3 interactive sections in diamond shapes are designed as the touch-sensitive buttons, and then the illumination of the cushion will be activated by touching the diamond areas. Similar design principles and weave approaches have been applied to cushion Sensi, and a different appearance and texture has been achieved. And this is to show you how the interactive function works with the designated areas, and then the illuminated views of these 2 interactive cushions. And then the final design challenge is during my study is to develop PUF textiles for the multi-sensory environment. So this project is collaborated with a Dimension Care Center in Hong Kong. A diversity of tactility and appearance was created for this interactive panel to provide sense stimulations to benefit the elderly through visuals and touches. So double weave and novelty yarns are combined to create distinct textures for the PUF textile pieces. And the motif designs were co-created with the social workers and elderly in the care center, which reflects nature and local cultures. The versatile of the PUF textiles became effective stimulations to trigger positive emotions for the elderly. So to sum up my work, so interactive polymeric optical fiber textiles serve as flexible illuminative materials, and it provides a dynamic visual appearance with its unique illuminated quality. So with the advantages of lightweight and flexibility, so optical fiber is a very suitable material and can be fabricated through traditional jacket weaving to achieve the interactive and illuminated functions. And then the new weave design approaches can bring enhanced properties and performance for the PUF textile, as well as more seamless electronic integration methods. Okay, so that's the end of my presentation, and thank you very much for your attention. If you have any questions, I'd love to answer them. Yeah, thank you.
Thank you very much for your presentation. I am sure everybody enjoyed the discussion, particularly on the designs that are possible on the jacquard with the optical fibers. Do we have any questions for Dr. G? Okay, do we have any comment, any suggestions on the presentations that have been presented today? Thank you very much, Dr. Lanji. We will definitely get back to you in case we want further information on your projects. Thank you very much.
Thank you.
The time now, it brings us to the end of the session, and we are supposed to take a break. And this break, I think if you have your program, it will be possible for you to see the link to the break. Okay, thank you very much.
which means that the wave superposition can be strengthened in our predetermined working frequency range. When the antenna was loaded by AMC, and the results show that there is no significant variation for the return loss, and the radiation pattern shows higher front lobe and lower back lobe. For the last part, let's take a look at the on-board antenna radiation performance. This work was done by simulation method. We put the simulated human tissue with determined dielectric properties below our previously designed slotted antenna. After calculation, we got antenna radiation properties and psi value as well. Here we have not loaded AMC on the antenna. The psi value was 256 watt per kilogram, which is much higher than the requirement of lower than 2 watt per kilogram. When AMC was loaded, the on-body return loss restored to the normal state and higher gain could be obtained. Also, psi value was 0.23 watt per kilogram, which was much lower than 2 watt per kilogram. For our conclusions, there are 3 main conclusions here. First, the miniaturized antenna patch had 24.5% decrease in area with 7% higher bandwidth. The second conclusion is when AMC was loaded, the off-body antenna had lower back lobe and higher gain. The third conclusion is when AMC was loaded, the on-board antenna had psi value of 0.23 watt per kilogram. Finally, if you are curious about the future change of variables, I list several items here. Maybe in the future, variables can extend your sensory function, and at that time you will have powers of clairvoyance and clairaudience. Who knows? Powers of clairvoyance. That's all for my presentation. And thank you for your attention. Who knows? Powers of clairvoyance. That's all for my presentation.
Thank you very much for your presentation. Now, can we take some questions from members who are around? Then we go to the last one by Tang Yi on peptide prerodent injectable and self-healing hydrogel for antibacterial wound dressing application. Ting E, he was allowed. Is he still around? Ting?
婷，现在轮到你了。
Yeah, okay, we can hear you. Can hear you now.
好，那我开始了。
Okay. Can you share your presentation, please? And Professor Lan, you can remove your presentation. You can. Okay, thank you.
Okay. Can you see the?
Yes, we can see it now. It's there.
Okay, I will play it.
Yeah. Okay. Start.
Hi everyone, I'm Ye Tingting. Today, my topic is peptides preloaded injectable and self-healing hydrogel for antibacterial wound dressing application. I will introduce my project from the following aspect. First, the research background. A skin defect caused by physical, chemical, and thermal injuries or physical diseases called wound. May challenges contain bacterial infections and poor wound healing. Poor wound healing is often caused by bacterial infection that causes exudate to form, greatly impeding wound healing. Due to the reduced activity and level of endogenous growth factors, chronic and deep wounds are difficult to angiogenesis and self-repair. Wound healing is a complex process, including 4 stages, namely hemostasis stage, defense inflammation stage, proliferation stage, and maturity stage. The location of the wound, the risk of infection, and the characteristic of patient all affect wound healing. The types of the wound dressing can be shown as follows. Hydrogels are excellent materials for wound dressing application due to their excellent biocompatibility, good mechanical properties, and a unique 3-dimensional structure. Injectable hydrogel can encapsulate cells or drugs, absorb liquid, fill the area of irregular wound, and be adhesive to the wound. But for irregular wound site and deep wounds, conventional injectable hydrogels lack self-healing ability and are easily damaged by external forces, which is not conducive to wound repair. In 2001, an article published by Dr. White in Nature first proposed the concept of self-healing, drawing people's attention to the superiority of self-healing materials. As for improvement, self-healing hydrogels can repair the rupture of hydrogels through the generation of dynamic covalent and non-covalent bonds to extend the stability time. In recent years, the mechanism of self-healing hydrogels is mainly to construct hydrogels by using dynamic chemical bonds, such as shape-based bonds, and so on. When these hydrogels are ruptured by external forces, the broken dynamic covalent bonds will recombine to hinder the rupture of hydrogel, reducing the frequency of hydrogel dressing replacement and accelerating wound repair. Second, preparation of injectable hydrogel. In this study, the tissue adhesion ability of dextrin was improved by modifying dextrin. First, the aldehyde group of oxidized dextrin was reacted with the amino group on the fatty amine to synthesize a partially alkylated dextrin. Second, the method of solid phase synthesis was used to synthesize new peptides that can stimulate the wound healing. Peptides vary with type and number of amino acids and the order of arrangement. Third, oxidized dextrin and alky-modified dextrin were dissolved in PBS solution, mixed according to a certain mass ratio, preloaded with a new peptide to prepare hydrogels. Finally, the hydrogels and non-woven fabrics were combined to prepare hydrogel fabric composite materials. The chemical structure of oxidized dextrin was characterized by HNMR, which was illustrated in Figure 1. The new characteristic peaks at chemical shifts between 4 to 6 ppm from ODX were attributed to hemiacetyl promoters formed by aldehyde groups and adjacent hydroxyl groups. In addition, there is a small new peak at about 9.3 ppm, indicating the presence of a very small amount of free aldehyde structure. The peaks of 2.1 ppm and 1.32 ppm of dot-cell tail were observed in HNMR spectrum of alkyl-modifying dextrin, indicating that the DOD was successfully prepared. Besides, the FTIR spectra of ODX was shown in Figure 2. The new small absorption band at 1738 was attributed to the symmetrical vibration of aldehyde, reflecting the effect oxidation of dextrin. Subsequently, hydrogels were prepared with different feed ratios, as shown in Table 1. By changing the feed ratio, the fastest generation time was 1 minute. It could be seen that higher content of ODX under certain conditions causes the fast gelation. That is because with the increasing content of ODX, the concentration of alkyl groups participating in the reaction would be higher, leading the reaction faster. Third, characterization of injectable hydrogel. Photos of injectable and self-healing hydrogels were shown in Figure 3. To confirm the morphology of hydrogels, the internal morphology was shown in Figure 4. The porous sponge-like structure was observed in SEM images of the freeze-dried hydrogels. Moreover, the pore size of the hydrogel made by ODX, ADH, and DOD was larger than the pore size of another hydrogel. This was because some of the aldehyde group on the oxidized dextrin reacted with the amine, resulting in a decrease in the number of aldehyde groups which could participate in the cross-linking of the hydrogel. In other words, the increase in pore size was attributed to the decrease in cross-linking density. The risk of infection, the location of the wound, and the characteristics of the patient would have an impact on wound healing. Therefore, the preparation of antibacterial hydrogels is significant. E. Klein and S. aureus were used as the test strings. The antibacterial properties of self-healing hydrogels were detected by the method of counting the colonies, as shown in Figure 5. It could be seen that under the influence of the hydrogel, the numbers of colonies decreased with time, and the antibacterial effect was most obvious at 4 hours. The antibacterial effect of DOD, ODX, and ADHP was better than another one, because the peptides contained in the hydrogel had antibacterial effect. For conclusions, in summary, we designed and prepared a multifunctional hydrogel that integrated the functions of antibacterial, self-healing, and promoting wound healing. The hydrogels and non-woven fabrics were combined to prepare hydrogel fabric composite materials. Besides, the prepared hydrogel was preloaded with synthetic new peptides to stimulate wound healing and improve the antibacterial properties. By modifying dextrin, the hydrogel had good tissue adhesion. Studies have shown that the prepared hydrogel has good antibacterial properties which can reduce the chance of wound infection, and its dynamic self-healing properties can be applied to irregular wounds especially. The injectable and self-healing hydrogel preloaded with peptide would have good potential for wood dressing application. Here are the references. Thank you all for coming and listening. That's all.
Thank you very much, Ting Tang, for the presentation. It was very clear. So that if you'll be around and there will be some questions, you can ask members to ask you 1 or 2 questions. Members, is there anyone with a question? Question, please. If there is no question, can you unmute yourself and say something?
What?
Dear Chair, can you unmute his?
Yes.
Yes, I think.
He wants to say something.
Well, yes, he is here, but I'm not sure whether he can. His microphone is working or not.
Yes, it works.
Okay. Can you say something? Okay, it's work.
Say something. Say what?
Okay, there's nothing to. We wanted to see if there's any question. If there isn't the question, it's okay.
Any questions?
I think there's no questions, and we thank you very much. I don't know what was. I think that comes the end of our presentation. Unless if somebody is having any other information we want to test. Thank you very much.
Thank you.
Dear Chair, there is one speaker. He wants to give a presentation, and now he's in our meeting room. He's Asbali. That's it. Yes. And do we have time to play his video? Because he missed his time. Okay. Thank you so much.
You can do the presentation. Can you go on?
Yeah, we can. Thank you so much.
Okay, you can share. Okay, it is there now. You can be able to continue can play it or the presentation. Please continue.
Maybe he should unmute himself first, Chair.
Can you?
Sorry. No, we couldn't hear.
张一霞，刚才可以的呀，你怎么关掉了？刚才有声音。
Can hear you now. You can hear you now.
不是，你等待一下，有点慢，你就把刚才的整个过程操作一遍。好，再来一次。
Can I continue?
Can you roll your PowerPoint again, please?
Yeah.
Yes. She will try again.
Okay.
Thank you very much giving this chance, especially for Professor Pinchu initiating me to present our research paper on this 4th Sino-African conference. The title is Effective Treatment of Mechanical Property of Unidirectional Insert Fiber Reinforced Polypropyl Composite. Me is a Subalo Desi, Pata University, Ethiopia. PhD students, Professor Pinchu, Donga University, China. Dr. Kedion, Bab University, Ethiopia. Liu Fanzi, Donga University, China. Why natural fibers are important compared to synthetic fibers in composites? Because of natural fibers have a silent future, low density, eco-friendly, lightweight, strong, renewable, cheap, biodegradable, good thermal insulation property, and high damping performance. Even though the fact the natural fibers such silent features, there is a limitation for reinforced composites. The limitations, the constraints are moisture absorbency, variability, weak matrix fiber interfacial addition, and poor fiber distribution. These properties are constraints to apply the natural fibers for composite application because this property retards its application. The fact that the natural fiber is strong polarized and the polymer hydrophobic property so that the interaction between the natural fiber that is and the polymer matrix hinder the efficiency of the interaction. So to improve the property of the natural fibers, that is the fiber modification is a technique. We have different techniques. One of the techniques is physical methods, the corona treatment, plasma treatment. The second one is surface modification, that's chemical methods, the sealant treatment, alkali, acetylene, and enzyme treatment. And melated coupling is the third maleic anhydride polypropyl. These are some of the modifications that used to improve the natural fiber property to use the composite application. Surface treatment and fiber orientation. Related to this research, all previous study to attain high tensile strength in unidirectional composite focus fiber yarns, spoon yarns, hybrid yarns, wrap yarns, woven with small to medium twist insertion and surface modification. So, limited study on insert woven mat in warp direction, polypropyl, and in wave direction a number of bundle fiber free from twist and surface modification with various levels has been done. Insert ventricles of insert fiber family Musa and its genus name insert. The main staple food of cold quoted from this insert fiber, that is from pseudostem, and also it is used as the staple foods. Almost 20% of Ethiopian peoples used as a staple food, and it is a round grain, tree against hunger, or that is future drought resistance crop insurance against hunger, and it is estimated about 50 million kilograms per year in that fiber from local supply. And the fiber yield efficiency from pseudostem is study indicated 6.3%. The high amount of the residual fiber not properly utilized and limited research was done. You can see that this is the plant fiber and this is the plant which is taken from the insert fiber and it is subjected to the fiber extraction knife, and this is the output of the insert fiber, that the residual, that is the insert fiber. The research is focused that its study and characterization of insert fiber with various chemicals, 3-glycine, oxyl, propylene trioxyl, GPS, and bis 3-toxyl propylene tetrasulfide on insert bundle fiber. And therefore, the development of treated and untreated woven mat unidirectional reinforced PP, well fabricated by compression molding and characterization. And the physical and mechanical properties are here. You can observe that at the bottom within summary. The surface treatment of sealant. The surface treatment of sealant with 100 mm of distilled water was poured in a beaker along with ethanol 50 to 50 weight to weight, and the two chemical sealant 6-9 with 3 levels 0.51, 1.5, and the GPS 1, 2.5 and 5%. And the procedure of the treatment is clearly put from 1 to 8. You can observe that fiber. The second one is determination of the tensile strings for insert fiber. The ISO 2060 standard test method are used, and universal strings machine is selected, and 60 samples are taken. The gauge length is 250 and speed 250 mm per minute, and the load cell 130 is selected to test the treated insert bundle fiber with various sealant chemicals. You can observe that these are the labeling of insert bundle fiber treated with various chemicals. Here are just insert woven mat manufacturing for composite application. You can see that using a mini weaving machine in warp direction, that is polypropylene, and in warp direction you can observe that the bundle fiber, and the output of the mat, that is woven mat, you can observe here. The development of unidirectional composite. The unidirectional composite development can be formed as the PP film matrix and insert fiber mat. The insert fiber mat 30 cm unidirectional woven mat, which was subjected to a surface treatment, that is the GPS and the sealant treatment, to enhance the strength of the composite. And before the compression molding, of course, it should be set oven dry at 70 degrees centigrade for 12 hours. And the plate dimension is specified for stacking arrangement, and the basic parameter in compression molding: temperature 190, time for 6 minutes, and pressure 9. The characterization of unidirectional composite, that is to test the unidirectional composite, STMD 638 is selected, and tensile universal strength machine and load cell capacity in km. The gauge length is 40 mm and cross-head moment 5 mm. And the composite also, the dimension is clearly specified. This is the machine specification, this is the composite application, and the number of samples all are included according to the procedure. Coming to the surface chemical analysis for transfer infrared spectroscopy model with FTR 660 type instrument space spectrometer were used, and the finely cut fiber sample were taken from the unidirectional composite and were mixed with analyzed grade KBR at a ratio of 1 to 100. And coming to the water observation tests, that is, it is investigated by STM D57 standards. The sample dimension is 20 mm times 20 times 2.6, and were dipped into a beaker of water at room temperature. And the evaluation system in the sample were weighing 0.001 milligram regularly at 3 days, 6 days, 9 days, 12 days, 50 days, and 80 days interval. You can, this is a sample, that is, this is a beaker, then sample put in the beaker, and the evaluation within this. Coming to the sealant treatment. you can see the graph that the higher tensile strings in unidirectional composite treated in sealant 5% weight of GPS and 1.5% of sealant 6.9 lead to the interaction form. A bridge brought an outcome of the development of hydrophile property of the fiber. You can observe that the sealant and the GPS is the highest tensile strings, and next to that the other will follow. The sealant coupling agent between, that is the elements, that is the interaction between the fiber and the sealant form a covalent bond. The sealant treatment, you can observe that the interaction between the sealant, the mechanism, you can observe that the sealant forms after hydrolyzing with water and alcohol. It forms silanol. This silanol can interact with the OH groups. So by considering the relative comparison from each level of surface treatment, GPS 5% and sealant 6.9 1.5, or select relatively better result will follow to the unidirectional composite. The mechanical property of unidirectional composite, you can observe that the mechanical property of unidirectional composite surface treatment of sealant 6.9 1.5, the highest tensile string is recorded, and it increased 102.78, 41.3 and 22.38, that is respectively, that is 102.78 from random, 41.3 from the unidirectional, and 22.3 from the GPS sealant. You can observe that the maximum tensile strings of the composite is recorded in sealant. The interaction, the case of this is the interaction of the functional group at one end with insert fiber of hygroscopic part and the other into the matrix of the hydrophobic group, forming a bridge between the fiber and the matrix, and that is establishing a covalent bond. And this form an outcome of growing the hydrophobic property of insert fiber. This is treatment is evidenced by other researchers. Different texture. Comparing the result of this unidirectional to the previous work, the flask yarn is the flask yarn aligned, flask aligned, and the flask canap, hemp, and insert fiber. It is comparable to the previous work, and the good result is achieved even with minimum fiber contents. The FTR result, that is the treatment of insert bundle fiber with sealant and the untreated, or in comparison to the untreated, it is visible that the peak variation, that is, that it indicates that the removal of the hemicellulose, the lignin, the peaked in each wavelengths indicated in the table. You can observe that, for instance, at 2374, that is the carbon triple bond, it indicates that in untreated fiber. After treatment of sealant, it is removed both in GPS and sealant. Similarly, you can go to the last, that 175 to 65 wavelengths, that is the complex structure, the sealant group, the condensation reaction between insert fiber and coupling agent is carried out at these wavelengths. In general, we can say that it is an indicator that the removal of the impurities is observed in the peak. The water observation property of the composite, you can observe that the water observation, that is, it is taken that from 3 days to 8 days, and the sealant group, that is sealant 6.9 1.5 treated recorded the highest resistance of the moisture immersion property in comparison to the other. That is, it reduced water observation 54.37, 31.2, 15.78 from the untreated unidirectional, from the untreated random, the GPS 5% treated respectively in relative to untreated unidirectional. This indicates that the good interaction between the fiber and the matrix with the absence of weight. This leads to the improvement of mechanical and dimensional properties of the composite for long-term performance can be reached. You can observe that the fact that here is the treatment of the sealant. Just the physical observation during 80 days, that is the physical observation, water observation, all samples are dropped down to the bottom of the beaker after soaking time of 6 to 8 days. But 1.5 weight of sealant 69 were floating for the last 80 days. Coming to the conclusion, insert treated with 5% GPS and 1.5 with sealant 69 observed slight increase in tensile strength compared from untreated. A composite manufacturing from 1.5 with sealant 6 of insert woven mat with a unidirectional polypropyl gives highest tensile strength with a percentage increase in 102.78 from random and 41.3 improvement from untreated unidirectional. And this result is supported by FETR spectroscope confirms the incorporation of sealant treatment with the fiber. The composite made of insert fiber treated with 1.5 of sealant 69 and 5% GPS increase elongation at break 34 and 11.9 respectively compared from untreated. Moreover, investigation of moisture observation indicates that insert fiber treated with 1.5 sealant 69 has a minimum water immersion compared to GPS 5% treated and untreated. And insert fiber treated with sealant 6 1.5 and GPS 5%. The fiber bundle arranged in a group of bundle fiber to form zero twist angle in inductional composite achieved promising highest mechanical property. Generally, you can recommend that this is a very good fiber used as a staple food as well as the residual used as an input for composite application. So a promising future for household furniture and building constructions. These are my reference. This is the
Okay, thank you very much, Daisy, for the presentation. Thank you very much, Daisy, for the presentation. I don't know if we have few minutes. If there's anybody with a question to Daisy's presentation about the fiber. You can raise up your hand or you can just unmute and ask a question.
Roger PTRE. I was interested, are there any environmental challenges with the treatment process, that you were describing in your lecture? Are there any harms or with that process?
Daisy, we can't hear you. We cannot hear you at all. Yes, we are hearing something, but can you increase the volume? We can't hear you. We can't hear you. We can see you, but you can't hear you.
Oh, sorry, maybe there's some problems with his microphone. We are contact with him to ask him whether he can answer the question or whether he can tap in the chat window.
Yeah, but if there is somebody who is working with him, from China, you can be able to answer the question from Rogers. The Rogers is asking any problem of environmental.
Yes, I'm asking somebody to contact with him. What's the problem with his microphone?
Okay. There is another hand. Can we get?
Maybe others can ask any question, another questions. Then Isabel can answer together.
Any other question, please, Rogers? Anybody else with a question? Then, if there is another question, we just agree that the question shall be sent to Daisy so that he can be able to answer, because we can't hear him, or I don't know whether he has written anything from the chat. Nothing even from the chat. Okay, so if that is so, then we say that the end of this session. And there are some other posters which are going to be going on in the link. If you can click at the chat, there are some other sessions of exhibitions which are going there. So we'll meet again. Yes? We'll meet at around 2 o'clock Kenyan time. That is 14 hours Kenyan time. I don't know the other time in your place. So we are about 3 hours before plus 3 GMT. So you can be able to join with us at that session. We are having an interactive session. Thank you very much, Daisy, for the presentation, and thank you very much for all the presenters in this session. And we wish you a nice time. Stay well. Thank you very much. Bye.
Thank you, Chair. And just now, Isabel said she will answer the questions through email. Welcome others to give the questions through the email. Thank you very much.
Okay. Thank you very much. We will communicate through the email. Thank you, Daisy. Thank you very much. Bye.
Goodbye.
Bye. Good.
just a small project I was doing. So now this is the Arduino microcontroller. Professor Isaac Koskea, the Vice Chancellor of Moi University, and I would want to welcome all of you to Moi University, to the Center of Excellence, what we call AC2, in phytochemicals, textiles, and renewable energy. This center was established in 2016, and so far we're doing very well. And we've achieved a number of benefits to the university and the community. The first being the incubation center, worth 25 million Kenya shillings, the only center in Kenya, and indeed in East and Southern Africa. Secondly, we bidded and won to develop a curriculum on energy access funded to the tune of 8 million Kenya shillings, which is ongoing. And again, we have innovations, a number of them, through AC2. Again, we've equipped our labs for teaching, training, and research. We've also given scholarships to a number of students who are doing postgraduate, 69 master's students, 27 PhDs. And we'll also undertake outreach services. In particular, we train on natural dyes in Gishu, Transoya, and Kisumu, and Ahero. We've also trained on renewable energy, where we've also installed biogas, in particular in cases in partnership with our Biogas International.
The Center of Excellence in Phytochemicals, Textile Engineering, Industrial Engineering, and Renewable Energy at Moi University, ACE2 PTRE, was established after a successful application of World Bank funding during the African Center of Excellence 2 bidding by East and South African states. It is one of the 24 African Centers of Excellence founded by the World Bank ACE2 project that aims to provide high-quality training and research within the African region.
Professor Ambrose Kiprop. I'm the Africa Center of Excellence in Phytochemicals, Textile and Renewable Energy Center leader, which is based at Moi University. And this Center of Excellence at Moi University is having 3 components: the phytochemicals, the textile, and the renewable energy component, which is addressed by 2 schools, the School of Biological and Physical Sciences, and also the School of Engineering. And we have 5 degree programs that we are offering at the center, and the training is for both master's and PhD programs.
The center has enrolled a total of 96 students. Those who are nationally drawn pursuing their master's courses are 34 male and 16 female, while 17 male and 6 female are pursuing their PhD courses. 30% of the students are from regional countries such as Malawi, Zambia, Uganda, Ethiopia, Rwanda, Sudan to Tanzania.
Bongomin Osiden. I come from Uganda, and I'm pursuing a master in industrial engineering. I'm in my final year.
I am Tandio Alidi. I am from Malawi. I'm studying MSce in analytical chemistry.
My name is Clement Malanda. I'm from Malawi.
My name is Lasaz Winfred, a student from Uganda pursuing a master's degree in analytical chemistry.
11 male and 7 female are pursuing master's courses, while 3 male and 2 female are pursuing the PhD courses.
We have received applications recently for this academic year starting 2019-2020, which also have students from all the way from Zambia, Malawi, and Ethiopia again, among the other countries that they had also applied last year.
Cognizant of the fact that some students hail from non-English-speaking countries, the Center, in partnership with the School of Arts and Social Sciences at Moi University, ensures that they are well trained to comprehend the language and better their reading and writing skills.
And then this course just basically means, how do you share the knowledge you're learning? or the knowledge that you're relating, that you're teaching. You can do that in two ways. You can do that in a written form, or you can do that in a
hybrid energy systems, energy systems modeling, optimizations and analysis, energy and environmental management, waste to energy, energy systems integration, energy storage, energy economics, policy and regulations. Welcome to Symposium 2. The theme of this session is renewable energy. The presentations will include smart technologies for energy access, energy conversion, hybrid energy systems, energy systems modeling, optimizations and analysis, energy and environmental management, waste to energy, energy systems integration, energy storage, energy economics, policy and regulations.
The Africa Center of Excellence in Phytochemicals, Textile and Renewable Energy, based at Moi University, Kenya, focuses on the manufacturing sector. It was established after a successful application of World Bank funding during the African Center of Excellence 2 bidding by Eastern and Southern African states. Its main objective is to train highly skilled manpower in phytochemicals, textile, industrial and renewable energy through research, innovation and technology transfer for enhancement of the manufacturing sector. As a regional center, PTRE missions focuses on providing highly trained, skilled and empowered human capacity with the potential to develop innovative products of high value and quality, offer services and solutions for the manufacturing sector. Currently, the center supports 3 PhD programs and 4 master's programs with a total of 141 students admitted from African countries. The center has developed and offered 3 short courses on program development and curriculum delivery, application of natural dyes, soap and detergent making. It boasts of 35 publications and has engaged staff and PhD students on an exchange program. ACE2 has also organized and participated in several events that foster partnership with the industry. They include biogas training for high schools, professional talks in the thematic areas, industrial linkage committee meetings, joint workshops with partners, biogas training outreach at Kesses Eldred, and self-evaluation workshops. The Africa Center of Excellence in Phytochemicals, Textile and Renewable Energy.
Welcome to Symposium 2. The theme of this session is renewable energy. The presentations will include smart technologies for energy access, energy conversion, hybrid energy systems, energy systems modeling, optimizations and analysis, energy and environmental management, waste to energy, energy systems integration, energy storage, energy economics, policy and regulations. Welcome to Symposium 2. The theme of this session is renewable energy. The presentations will include smart
we needed to make sure that the chain converges, and to help us ascertain whether the chain converged or not, we had to have a trace plot and an autocorrelation plot, and there are graphs as we see on the screen. Now, the parameters we estimated as follows. We see that the true value for the intercept was 1, the slope was 2, and the variance was 1.0. Now, INLA estimated the intercept as 1.281, whilst MCMC estimated the intercept as 1.283, and both of them had a standard deviation of 0.11. If we consider the slope, which is beta 1, we see that MCMC estimated the slope as 2.097 with a standard deviation of 0.12, and INLA estimated the slope as 2.0